Well, let's talk about watershed modeling. This is just kind of a overhead view of what we're going to be doing with WMS, because sometimes people get the wrong idea of what the program is and how it operates. And so I wanted to begin by taking a step back. Since we had that week of suspension and then the spring break, it's kind of hard to even remember where we were or what we were doing this semester. But remember that the big question of this course, what we're trying to do as hydrologists, would be to define what the runoff is going to be for an area of interest. And so that area of interest could be an urban neighborhood. The area of interest could be a rural watershed where we have flow going through a creek, and now we have to understand how deep is the water going to be in that creek. Or we may be interested to find out what is the flow rate through a culvert, for example. And so I think someone just got their audio working here. Let me mute it though. There we go. Oh, you're calling in. That's great. Okay. So the runoff characteristics that we want to know is how much flow and over what time. And remember that the inputs to that, we talked about rainfall and different data sources for obtaining rainfall information, like the precipitation data frequency server. And we'd like to know not only the depth of rainfall, but also when it's occurring. And that's the temporal distribution, the over time, how much rainfall is coming out of the sky. And the spatial distribution, meaning, over a really large watershed, it may be the case that we don't have a uniform rainfall depth, that at certain locations on a map there's more rain than in others. Abstractions, remember, are things like the surface wetting effect, forest litter. It could be the interception from vegetation and trees and plants. We want to be able to characterize the effect of infiltration. So looking at the nature of the soil and the ease of water flowing through it, as well as how moist the soil was prior to a storm beginning. And so those things go up into characterizing the curve number. And then this is where things get interesting, where we have all this input data and we want to determine the runoff. And specifically, we're going to try and look at the shape of the hydrograph, the peak runoff amount, and some of the simplest methods that we use to relate rainfall and runoff was the rational method. And we'll talk about that a little bit today as one of the methods that WMS can run for us. And routing is the effect of water travel times, so the travel time it takes for water to be flowing over the surface, or if it begins to channelize, or if the flow is going through a stream. And then finally, using that data to do things like sizing culverts, sizing channels. And unfortunately, because of the week of suspension, we're not going to be able to get into the risk assessment and kind of the floodplain management part of the course. But that's one of the things that hydrologists would do, is take the results of a watershed model and then try to estimate how much it's sensible to spend to protect against flooding. WMS, Watershed Modeling System, is not itself a hydrologic model. It's a model pre and post processor. And so as a preprocessor, what that means is that it goes and gathers the data that all these other methods need. And nowadays with the internet, it's relatively easy to get the data, but there's so many different sources that it's in that, even though it's all there for the downloading, finding the right website, and especially because these government websites seem to change about once a year, like the address and the format that the data is in and what you have to do to get it. So WMS has some nice functionality where they keep up to date on what the server is, and in some cases they're actually caching the data from the server. So that means, like for a digital elevation model, they'll go and download the entire United States at all the resolutions available, so that if you were going to get the data from the government, it may be one of the things where they want you to put in your email address, and then they're going to put you in the queue so that maybe several hours later it's finally your turn to download the data. Well, Aquaveo and WMS, what they'll be doing is they'll go and get all of the data from the government websites, and then they have it on their own intermediate servers so that you don't have to rely on them to obtain it. So WMS is a preprocessor, meaning that it obtains the data, and it's a post-processor, meaning that once it runs the model, you can use WMS to make graphs and visualizations of what's happening. But the models themselves weren't developed by Aquaveo. Aquaveo is using government-developed models, or just kind of concepts that have been out there a long time, like the rational method. And so this is listed in kind of increasing sophistication, different ways of estimating what is the runoff coming from a watershed. And so rational method we've talked about before, where we're just trying to calculate the peak runoff from a storm, where the C value, the rational method C value, is related to how much impervious area there is, and it's kind of, as Doug Kirk mentioned when we were having our last class meeting on the 13th prior to the classes being suspended, it's a little bit tricky to look at an area and know something like what's the Manning's N or what's the rational method. The rainfall intensity we assume is going to be constant, and that's one of the big weaknesses of the rational method, is that built into that method is the idea that you're going to be estimating the peak runoff from some constant rainfall intensity. But it's never the case that a storm starts at its rainfall intensity and stays that same intensity until it immediately stops. And so the rational method generally overestimates, and not only does it overestimate, is that it's only as good as our capacity to characterize the C value. And so we've looked at these tables of C values before, and we can try and make adjustments based on how steep the surface is or how good of condition the vegetation is within a watershed. But there's not really the same kind of repeatable and scientific means of estimating a C value as there is with a curve number. And so WMS, if we take this to WMS, there are data sources that we can rely on to estimate curve number, but not estimate C value. There isn't like a GIS overlay that has the C value estimated based on the land use and soil type. It's just kind of your best guess type scenario. So that's really the weakness of the rational method. Now, where things get a little bit more repeatable and defensible is where we move on to the national streamflow statistics. And that's one of the models that's built into WMS that allows us to estimate the peak runoff based on regression equations that the USGS has developed for each state in the United States. Well, I guess, what does it say here? None. I guess no. All the states have a national streamflow statistics. The most recent edition of West Virginia's statistics was published in 2010. And in 2010, what they did was they looked at all of the good rain gauges across the state and the stream gauges across the state, and they tried to relate the two. And so you can see that each one of these triangles is showing a stream gauge where they had good historical data, and they broke the state up into different regions. There's the eastern panhandle, where the geography and the weather conditions are really distinct to the rest of the state. There's the central mountains, where the state has more higher elevation, and then the Western Plateau, which is what Cabell County is in, the Western Plateau region. And there's a different set of equations for each of these regions. And here in West Virginia, the regression equations are just based on the area of the watershed of interest. And so, for instance, if you're in Cabell County and you have a watershed of a certain size, then you can put that watershed into a regression equation and calculate what would be the peak runoff from that watershed for a certain size storm. So, for example, this is really the meat of that document. The document itself, I don't know, it's about 100 pages long, where they talk about what all of their methods were, what are the different gauges that went into the analysis, what's like the statistical quality, depending on how many years of data that they had and how many observations and how far apart the rain gauges and the stream gauges were. So, that's the report goes on and on and on, but then like the actual equations that you use only takes up really a single page. And so here's just a look, for instance, in the Eastern Panhandle region. If you wanted to know what is the 25-year storm, so PK25, the 4% annual exceedance probability means that in any given year there's a 4% chance that you would see this particular storm. So the equation is 204 times the drainage area to the 0.848 power. And you put the drainage area in square miles, and then it's going to tell you the discharge in cubic feet per second. And so it's just that easy. Now, that's for West Virginia. Not every state has such a simple regression equation. Where they have better data, or there's more geographic variability, sometimes these national stream flow statistics equations will take other things into account besides just the drainage area. For example, I'm pretty well acquainted with the equations for Arizona, and in Arizona it actually uses the elevation of the watershed as another factor that goes in. And so it would be the drainage area is one component, and then the elevation of the watershed is another component. And that's because they have some pretty big mountains in Arizona, and they have observed that the elevation of the watershed, because of the orographic effects, has an influence on the intensity of the rainfall, and then that has an influence on the runoff. So for each of these different equations, you could find what is the 2-year storm, the 5-year storm, the 10-year storm, and what you're putting in is the area of the watershed in terms of square miles, and it gives you CFS. And then all the stuff over to the right is just giving you an idea of the statistical quality and what's your error going to be. And I mean, these errors aren't great. If you're trying to predict the 5-year storm, what this is saying is that in general, the average error for using this approach is going to be 27%. So that could be that you're overestimating by 27% or underestimating by 27%. But the reason why there's so much error is partly because they don't have a lot of data, because the rain gauges and the stream gauges are spread out across the state. But then the other factor is that this doesn't take into account what's actually in the watershed. Now, it's assumed that you're using this for rural watersheds, that it's not for an urbanized place like Charleston or Huntington, that these are out in rural areas, but still it's not taking into account whether in the watershed it has rock, how much clay there is, whether it may have lakes and a lot of streams where the curve number would be higher if you have open water. So it's just kind of only taking into account the size of the watershed, and it's assuming that within each region all the watersheds are the same. And so that's why we see so much prediction error. So let me pause for a moment and just see if anybody has any questions. All right. So, Jeffrey, on National Streamflow Statistics, do we use all the errors or we use a single error? Well, we don't use the errors. It's just that's the error that occurs. And so you have to be, it gives you an idea of maybe if you were using NSS, the extra safety factor that you'd maybe want to build into, say, the size of your culvert. So let's say, for example, what if you were going to be sizing a culvert, and you use this equation and it says that the peak flow from your watershed is going to be 100 CFS. Well, if the average error is 25%, then it may be a good idea to build the culvert to carry 125 CFS, just to be within the realm of conservative when it comes to national stream flow statistics. Are there any other questions about NSS? Okay. We'll also take some time at the end of the class in case there were any questions that I didn't happen to pause and look at the chat screen. Then maybe you can write down your questions and we can go over them at the end of what I have prepared. So that's national stream flow statistics, and so one of the things that WMS will do is it'll automatically calculate the drainage area for you, and then it will put it into the equation for you, so you don't have to do the math. You'll just tell it, calculate the 25-year storm runoff for me, and it'll do it in an automated, quick way. So that's NSS. Now, all the other methods on this list, so rational method uses C values. National stream flow statistics uses just the area of the watershed, along with this regression analysis having to do with the localized conditions. These other three methods use curve numbers. It uses curve numbers to define how much storage there's going to be, how much initial abstractions we're going to see. And so TR55, HEC1, and HEC-HMS all depend on your ability to calculate a curve number. And so just to refresh our memory on what the curve number approach does is we're using tables like this where we're dividing the soil up into soil group A, B, C, D, and A is those soils that drain more easily. D is a plastic or swelling soil, C is soils that have substantial clay amounts, and B is just kind of in between A and C. So the different soil groups and different land use covers, we'd get a curve number, and then from that calculate S, the maximum potential storage. And the idea of the NRCS method is that for a certain rainfall hydrograph, that there is this curve of declining potential infiltration. And so infiltration during a storm is going to be decreasing as the suction pressure decreases, then the rate of rainfall being absorbed into the soil goes down. And so what we're trying to figure out is how much rainfall depth is going to be above that line. And so the precipitation excess is the amount of rainfall, and all of these we're talking in terms of either an intensity or a depth. It's not a volume, it's just like an amount in terms of how many inches or how many centimeters of rainfall there is. So we're trying to figure out how much rainfall excess there is, and then we're spreading that out over the area of the watershed to find a volume. And then the timing of it, the width of these rainfall hydrograph bars represents a time. We get the temporal distribution from how long the precipitation excess occurs. And so the curve number model is what goes into each of these approaches and how they differ. The TR55 is the simplest of the three methods that uses curve number, and it doesn't really do any specialized calculations having to do with the duration of precipitation. You'd put in a rainfall amount, and then it directly applies the same synthetic approach for a unit hydrograph. And we've looked at this unit hydrograph curve before, where the SES unit hydrograph for a certain amount of rainfall excess, it distributes when that's going to be. And so it defines the shape of the curve where you're going up to the peak, and you calculate the time to peak by knowing different physical characteristics of the watershed. And so as we move into WMS, the nice thing that it does for us is we're going to need to know the curve number. So it goes and gets the soil type data. We don't have to go directly to USDA to get the soil type data. It knows which servers to use, and you're going to be defining a project area so that it can obtain that data on your behalf. And it will calculate, for example, the average watershed slope. It will calculate the storage based on the curve number. It will calculate the maximum hydraulic length that applies so that you know all of these physical parameters and are able to use the unit hydrograph. So let me now just quickly give you an overview of what WMS looks like. And okay, so here's the WMS program, and when you use it for the first time, you have to put in the license code that I gave you via email, and I'll send that out again in case you no longer have that. The other thing is that it may prompt you the first few times you use it, whether you, I just got one earlier as I was setting it up on this computer. It was asking me about should you edit the registry on the computer, and so I'll send you a brief video that you can step through to make sure that you have everything set up so that you can begin using it on Wednesday. But the hydrologic modeling wizard here is kind of the hub for when you're starting out to use WMS. It's this looks like, I guess that's a wizard cap. You know, it's called the hydrologic modeling wizard, and so it's a wizard cap on roller skates or something. But if you click that, and it takes you through a process. Each one of these is a different step in the watershed modeling process, and so you don't have to exactly remember the procedure in the way that you would if this wizard didn't exist. It tells you that the first thing you'd need to do is save your file and so on. But we're going to go in more slowly, and I'm going to have you doing these same steps later on. But just to give you an idea of what it can do, I'm going to give you a quick demonstration of it. So I'm creating a subfolder and then saving this, which is always a good idea because occasionally the program crashes. It was increasingly stable, but not 100%. So you have to actually click the save button here to make sure that it actually saves that file. And then this is the tricky thing. It's on the second screen that you would potentially get that registry editor message that I was mentioning earlier. A projection, I think some of you have probably taken an advanced GIS class and you may already know what a projection is, but different maps have different coordinate systems, and we have to tell it which coordinate system we want it to be using for all of the GIS data that it brings in. And so if you click here in the define, I think it probably as a default starts off with no projection, but the projection that we're going to use is we're going to have it do WGS 1984 Zone 17. Zone 17 is West Virginia falls within Zone 17. The different zones correspond to different longitudes, and so we're telling it that the project that we're going to be working in is in the longitude range that West Virginia falls in, Zone 17 North. And so you'll have to set that projection and then a datum, a vertical datum, and I think by default it might have the units in feet. And so if I just change these units to meters, because the data I'm going to download, the elevation data is in meters, and so over here you can see that now it's saying that the horizontal units and the vertical units are both in meters, which is good because otherwise we'd get an error message at a certain point. Now here in the boundary, this is another place where the first time you activate this tool, define the boundary, you might get a message and just accept the default, tell it okay, yes, you do want to edit the registry, and you may get an error message the first couple of times. Another thing that used to happen to me was when I'd start this tool, it would not come up in the foreground, like it would be in the background, and so you'd kind of have to click among the tabs here to finally bring it into the foreground. They may have ironed that out, that error message, but the first time you look at this tool, it probably has the entire world, and so you can zoom in manually, or sometimes they have this name server that works pretty well, and so let's just see if it knows where Columbus, Ohio is. Yeah, it does. Alright, so Huntington, West Virginia. No, it has no idea what I mean by that. Oh, no, okay, there we go. Huntington, West Virginia. So just to give you an idea of why we like WMS, what it can do for us that's so convenient. If I zoom in on a rural area outside of Huntington, and I see, okay, this looks like a watershed. The map that's in the background here, this street map, there's different map options available, but I can see, regardless of which option I'm using, there's a ridge line here. And previously I showed you how you could like trace that ridge line with Google Maps or Google Earth Pro. You can trace the ridge line, it'll tell you the area, and kind of manually get an idea of what's the area of the watershed, because here is the low point in this watershed, and it may be that there's a road that's going to be crossing that creek, and we want to know how big the culvert needs to be because there's going to be flow going through there. So the cool thing that WMS does is once we define that project area, based on where I zoomed in, the coordinates are defined by the edges, and so each of the four corners is defining how much data it's going to go obtain. And so I could zoom in a little bit further, like this is the watershed I'm interested in. Now it's adjusted these coordinates for the extent of it. And then its capability is it can use these web services to obtain the data that I need to run simulations. And so each one of these rows is a data source that it can automatically download specifically for the area that I am interested in. And so just to give you some of the highlights is it can go and get imagery like overhead aerial photos. It can get the topographic maps that will allow us to identify street locations and names of creeks and rivers and so on. What I have enabled here is elevation data, and I'll download that in just a minute, but the elevation data is going to enable me to automatically define that ridge line, and so that I can see the size of the watershed. Other notable highlights, NLCD, the National Land Cover Database, is a really great way to calculate the curve number, because this is a coverage that identifies what is in a certain area. So it will identify whether you have deciduous hardwoods, or whether you have agricultural land, or open water, or urban areas. And so it is basically on the curve number table, it defines the rows. So if we go back to the curve numbers, each of these different rows corresponds to residential areas, commercial areas, whether it's lawns and so on. So the National Land Cover Database is telling you what is in the land. And then we have different soil types, so that's defining the column on this table. And so the column's different hydrologic soil group. And so you can go and download the soil data, the land cover, and then there's a tool inside of WMS that will combine the two and calculate the curve number for you. So it's no longer kind of just guesswork and engineering judgment, or using your experience to estimate what the runoff is going to be based on a guess of what it looks like. This is defensible and it's repeatable, where two different people can do the calculation for the same area and have the same curve number. And that's kind of the level of certainty that you need if you're going to be doing design that stands up to rigorous evaluation, like say in a courtroom situation. So just for now, what I'm going to do is I'm going to download the elevation data, and it's only going to get the elevation data. If we go back to defining our boundaries, it's only going to get the elevation data for this region. And if I zoom out, I could have it get more elevation data, but it's just going to do it for this project window. And so click download the data, and it asks me, what resolution do you want? And I always just go with kind of the default, whatever it suggests. And the reason why it's giving you the question is if you have a really big area, it can thin out the data that it's downloading, because if you download really high resolution data for an enormous area, then it could take hours to download that. But because I'm zoomed in on a pretty small area, it's offering to get this high resolution data where each cell has a size of 3.7 meters, and that's talking about the horizontal distance. And so it's going to be assigning the same elevation to cells that are 3.7 meters in length. So click OK, and it gets that really quickly, and then when it does, you can see all of a sudden it's put some contours in the background there. So let me just close this for a moment. So remember what we were looking at in the project area. It was a watershed where the stream boundary was down here at the bottom. And so it's created a temperature map that's showing the ridge lines in red. It's showing the low areas in blue, kind of just to maybe draw to your mind where the river would be. And so it didn't create this by looking at the image file that I was viewing earlier. This is just only based on elevation. And so as I move my cursor around, I'm able to identify what's the elevation in each of those spots. But what's really cool is that WMS has the capacity to delineate the watershed for us. And so remember when we were talking about how you use Google Earth Pro, it was the idea as well, I'm going to manually just click along that ridge line, and then in the end it'll tell me what's the area. But what if I wanted the computer to find the ridge line and be more precise about it than I maybe would be, because I'm only going to click every so often, but the computer doesn't get bored clicking with really close interval spacing, and it will know exactly where the high ridgeline area is. And so back here to the wizard, if I skip through these first steps and tell it I want to use Topaz. Topaz is this little subroutine that analyzes in right now this elevation model. It's going to analyze where are all of the directions that water would flow. And so if a water droplet fell on this 3.7 by 3.7 meter cell, what direction would it flow? And the way it does that is it looks at all of the adjacent cells and it finds which of them is the lowest. And so if a raindrop falls here, it's going to start moving in the direction of what's the lowest. It's not going to go uphill, and it wouldn't go to the left, even if left is lower. It wouldn't go to the left if ahead of it, north, is even lower than the cell to the left. And so it finds what's the steepest path downhill. And so it basically assigns a direction for each one of those cells. And when I click Topaz, what it does is it draws where the streams are going to form. And I may have to adjust. Here I've done 5 acres. I'll show you what it looks like if I do just 1 acre. Then it's going to, these blue lines which represent where the stream is going to form, it's looking for where is there 1 acre of upstream area contributing to flow at a certain location. And so if all it takes is 1 acre of land to make it so that I start to see a stream, and that could be the case if it's really heavy rainfall, you may actually see flowing water this far up into a watershed. But if it's a lighter rainstorm, then it may be that there's surface flow for 5 acres, and then when there's finally 5 acres contributing to flow at a certain location, now we begin to see the streams. And so this is where the stream would be, and if we want to see what the map looked like, I can turn on a map just to bring it into the background there. So I've added a map and it's adding it here. Let me temporarily turn off the elevation map. So you can see here's the name of some roads, Little Cabell Creek. We don't see a lot because we're so zoomed in pretty far, but we do have the maps that we can turn on. But let me turn this back on. Okay, so these are the contour lines, and I've been bragging about how easily it can delineate the watershed. So if I want to know what is the area of the watershed, all I have to do is click where I want the crossing to be, like the location I just put, that outlet location would be our location of interest, where we want to know what's happening there from a flow rate standpoint, how much area upstream is there. And now that I've added that, if I click on delineate watershed, then it will go through and calculate all the contributing area for me. You can see at the bottom there it was giving a message as it was doing it. And so let me just move the symbol out of the way. Is it 74.4 acres, and so it has gone through and calculated the boundaries of the watershed automatically for us, and so it's a pretty cool little functionality.